All right, scholars, welcome. Let me charge this while I do my announcements. So yeah, guys, congratulations, right? You deserve a pat on the back, a round of applause. Woo, 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 woo. All right. That's my little sound effect button. Woo, woo, woo. Right. This is the last of the new material, right? The last of the new content for the semester. So let me pull up my calendar. Let me see. I think it should be okay. Right. So today is the 12th, right? The last of the new content. I think we have exam 2 that's going to become available this upcoming Sunday at 11:11 a.m. and it's due the following Sunday at 11:59 p.m. The last day of class, so all next week, we're going to be working on exam 2. I'll just kind of be going through answering questions, just really making myself available. More than likely what I'll do is just, get on the Zoom, take attendance. And then if you don't have questions, I probably more than likely won't keep you, but I'll probably stay on the Zoom. I might even stream a gaming session or whatever, depending on how it goes. So then the following week, April 26th, that Wednesday, that's the last official day of class, right? So then that Thursday and Friday, April 27th and 28th is the reading period. The schools should be closed. And then final exam week is that first full week in May. All right, so I think I scheduled your final exam to become available that Sunday, April 30th at 11:11 a.m. and it's due the following Friday at Cinco de Mayo at 11:59 p.m. Right? That's a critical time because that's a hard deadline for all assignments, right? So if you're going back over your assignments in Pearson and you're trying to improve your overall score, you definitely want to prioritize your exams as their value, they're weighted. So the exams altogether total about 80%, maybe just shy of 80% of your overall grade. I have to look at the syllabus to see our grading rationale. So if you're going back, if you're going back to work on assignments to improve your score, you definitely want to prioritize your exams. I know we've had one, we're about to have the second one, and then we're going to have a final. Yeah, you definitely want to prioritize the exams. Just you get unlimited attempts at these assignments. There's only a 10% late penalty. So even on exam one, you can still right now earn up to 90%. If you got a perfect score on exam one, you will get a 90% for that. With exam two, as long as you submit it by the deadline, you can earn up to 100. Limited attempts, minimal late penalty. What else? There was something else. Yeah, the homework and quizzes, that's kind of like a lot of work for a little bit of points, right? So to get the most bang for your bucks, the most return on your effort is you want to definitely maximize and prioritize your exams. Once your exams are wherever you would like them to be, then if you have the energy or the gumption, or if you feel inspired to, then I would do the quizzes, and then after the quizzes, only if you feel like it, go back and do any missing homework assignments. The homework is a lot of work for little points, right? So most of your points come from the exams. You're also welcome to take this content and work together, sit down with the tutors, right? You can take this content and sit down with the tutors and work on it with them. It's going to be okay, right? The real intent of this course, the way I have it designed, I'm really just trying to expose you guys to these concepts and encourage you to try your best, right? Devise a plan to get the stuff submitted. It's not an attempt grade, it's an actual grade, right? I take whatever's on Pearson, but you have a little bit of wiggle room there that you can kind of take advantage of. All right, okay. So as usual, if you have questions, feel free to unmute yourself to get my attention. Let me check on you guys in Zoom one more again. Okay, I think we lost maybe one or two, but it's okay. That's usual. This is not for the faint at heart, right? Even if we were in person, it's still about the same rhythm. It's still about the same. The only difference is, you can actually see my physical body. You're going to be physically next to your classmates. But being remote, it's not easy, right? You have to take initiative. If you don't have the ability to take the initiative, it's a challenge, right? So you got to devise a plan, and I give you a little bit of wiggle room. Like I do that on purpose because I think it's reasonable for this kind of setup, right? Okay, so hopefully you guys have been able to do something that's working for you. I think back, if I think back to the midterm grades, they did kind of make me a little bit nervous, but I've been noticing that with the remote, that's about how it goes. Going into the final, oftentimes the students have me nervous, but then they somehow pull it together. They just, do whatever they need to do to get it submitted, right? So that's been about what it's been teaching remote. So, we'll see how this goes. Hopefully, we can position as many people as possible for success. You guys can keep moving, and hopefully you guys can learn something from the experience. If it's not calculus, then something about something, about time management, or, being flexible or creative or hardworking or industrious or diligent, something. You should be able to get something out of this experience, right? Okay, so with that, let's take some time and let's take a moment to look at the this final content for the semester. So this is the last of the new content, and it's the last topic that we're going to talk about in chapter 4 of integration. And so this section is 4.6, integration techniques, integration by parts, right? So last time we went over a concept or a technique that was substitution, right? So this is like the complement, or this is like part 2 of the integration techniques. So we worked several examples using substitution. So here's another one that we have at our disposal, integration by parts. A few objectives here. We like to evaluate integrals using the formula for integration by parts and solve applied problems involving integration by parts, right? So integration by parts formula is, as you see here, right? Let's go like this. And this is so wild. I had about two hours before class started today, and I had been intended to get to the neighbor's yard. I was like, okay, I know it takes me 2 hours to do the yard. So I was like, well, let me just do what I can before class, and then I'll just stop. This is why I personally like remote. If I'm working on a project or I need to be doing something around the house, I can kind of work up until the last minute and then just stop. Versus being in person, now I had to commit all of my time and energy battling like traffic and the commute and cops and road rage, this that, and the other. The weather, it's a lot, right? So that's neither here nor there. Okay. So integration by parts, right? So when we go to evaluate an integral, what we're going to be doing is basically the integral of u dv equals uv minus the integral of v du, right? So we're going to be manipulating. Now, I'm trying to think of the derivation of this. I never thought about how to derive this guy. Let me think about it for a moment. Yeah, I'm not sure. I had to think about where this formula comes from, but for right now, we're just gonna work through and explore how to use this guy, right? I feel like this will be easier to explain by just working an example or two or three. All right, so let's kind of keep moving. Okay, so some tips on using integration by parts. If you had no success using substitution, then try integration by parts. We use integration by parts when an integral is of the form the integral of f of x times g of x dx, right? So we match it with the integral of the form u dv. By choosing a function u to be f of x, where f can be differentiated, and the remaining factor dv to be g of x dx, where g of x can be integrated, right? Then find du by differentiating, and find v by integrating. If the resulting integral is more complicated than the original, make some other choice for u and dv, and then to check your solution, differentiate, right? So again, we see that we use integration by parts when we come across something that's basically the integral of one function times another dx, right? So we're going to choose a u, we're going to choose a dv, and then we need to find du and find v, right? We're going to find du by differentiating, we're going to find v by integrating, and then we're going to try to evaluate the resulting integral, right? So it's a mouthful. Let's see it in action. Let's see. Why do I feel like something is missing? Okay. So here, let's try. Let me see. Okay, I'm just going to try something. So if we let u be what? The natural log of x, and if we let dv be dx, right? Okay, so let's try this. Now, we said let u be this and dv be this. Now we need to find du, right? So we find it by taking the derivative. The derivative of log is dx by x. And the integral of dx, I think that means our v would just be x, right? So integration by parts says what? The integral of u dv equals uv minus the integral of v du. That's integration by parts, right? That's how we apply it. Okay, so now if we fill in the components, so our u, and let's see, I mean, I could color code it. I feel like it's okay, right? So we have the natural log of x dx, right? That should be, now our u is going to be natural log of x. Our v is x minus the integral of v du is dx by x, right? So you should notice something, right? These x's should cancel each other. And I think this makes it much easier, right? So now we have x natural log of x. That's interesting. Okay. Minus the integral of dx, but the integral of dx is just what? X. So then, long story short, I think we can leave it as x natural log of x minus x plus some constant. Muy interesante. All right, so this is what we get. Now, they potentially might move this x to the power, but it's the same thing. Okay, let's see. Okay, so let u be the natural log of x, dv be dx. I think we got all of these components. Let's get rid of this for right now. x natural log of x minus x plus a constant. Okay, let's just do another one. All right, let's just do another one. Quick check, I'll leave as an exercise, and we have this guy here. Okay, I think we can do it. Let's see. So we're gonna let our u, I'm thinking natural log of x, right? Can we? And we're gonna let our dv, we're gonna let that be, I guess we can do x dx. Okay, so that means our du is gonna be dx by x. Our v, if we integrate, is gonna be what? X squared over 2. Okay, again, integration by parts is the integral of u dv equals uv minus the integral of v du. Okay. So then that means that our integral of x, natural log of x dx, we're going to rewrite it as, let's try it. Now we're just trying something. If it doesn't work, then we'll make a different choice, right? So uv, so we're going to have x squared over 2 times the natural log of x. So that's our u times our v, minus the integral of v, x squared over 2 v du, right? So times dx over x. Okay, let's do our simplification. So this x turns this 2 into a 1. We could just move that half in front of the integral. So if we rewrite this, we're going to have x squared over 2 natural log of x minus what, 1/2 times the integral of x dx, right? Now that integral is much easier to calculate than the original, right? So that's a good omen. So that means we can finish or we can keep going. So then we get x squared over 2 ln x minus, but that becomes what, x squared over 2. So it's going to become x squared over 4 plus some constant. Okay, let's just check our work really quickly. And that's supposed to be what? X squared over 2 right here. Okay, so we get x squared over 2 ln x minus x squared over 4 plus a constant. I just want to kind of jump to the end. There it is right there. X squared over 2 ln x minus x squared over 4 plus a constant. Let's kind of back up and see what kind of details that they have, right? So they said, let's examine several choices for u and v. So in our first attempt, they said, let u be 1 and dv be x ln x, right? This won't work because we don't know how to integrate x ln x dx, right? So they originally tried to let u be 1 and dv be this, but they couldn't integrate that, right? So on the second attempt, they said, let u be x ln x and dv be dx. This integral seems to be more complicated than the original, right? So after doing it, they eventually got to something like this, which was worse than where they started. So that was their second attempt. So their third attempt, which somehow by the good grace of God, we got it on our first attempt, right? That's the challenge with this is selecting a proper u and a proper dv. So then they finally realized, okay, let u be ln x, dv be x dx. So then du is going to be dx by x, v is going to be x squared over 2, and then long story short, they get to the same conclusion that we got to, right? But it was good that they showed that, because that does happen. Sometimes you choose a u and a dv, and it just doesn't work. So then you try choosing a different u and dv, and you you try substitution, integration by substitution. That doesn't work. You try integration by parts, choosing several different u's and dv's until you get something that works, if it's integrable, right? So, okay, let me pause for the cause and checking you guys in Zoom. Okay, let me get this student. I'm gonna let that sit there, and I got him right here. Awesome sauce. Make sure. Yeah, I got him. Okay. Okay. All right. So, integration by parts, U and DV. Okay. Okay. So with this one, let's see. Let's let our U. I'm thinking let U be the square root of 5x plus 1. And we're going to let our dv be x dx. Okay. So then that means our du is going to be what? 1/2 5x plus 1 to the negative 1/2 times 5, right? Because times the integral, the derivative of the inside. So times 5, I'm just going to put the 5 right here. Okay. And that's what is that? Dx. Okay. So that was basically the chain rule, the derivative of the outside function times the derivative of the inside function. And if we integrate our dv, then our v becomes what? X squared over 2. All right. Okay. All right. So then again, integration by parts. Again, so I'm rewriting the formula every time because one of my professors / mentors would say, you know, every time you use a formula, write it down. You know, that constant writing of the constant repetitive repetition of writing that formula ingrains it in your memory. Right. So as you work through examples, every time you use a formula, it's a good idea to just write it anyway. And that's how you learn it, right? So integration by parts is the integral of u dv equals uv minus the integral of v du. Okay. Okay. So then the original we had was integral of x square root 5x plus 1 dx. So now, based on the way we chose our u and our dv, now we're going to say u times v. So we're going to have this x squared over 2 times the square root of 5x plus 1. That's uv minus the integral of v du. Sheesh. Oh, that integral. That looks worse, right? That looks challenging. V du, if we say v du, yeah, that doesn't look any easier to integrate. Let me think about it. What if that was our u? What else could we choose? Let me think about this. If that were our u, so we need to say something times something else. What if that's our du? Can we integrate that guy? No. V du, right? That times that. Let me think about it. If I switch these around, if that was my u and that was my dv, the thing is, I don't think we can integrate that. Let's see, v du, if we plug this in, we're going to get what? 5/4 x squared over this. U dv. It looks like it's getting worse. What else could we choose? If that were my u, we can't choose that one. Let me see, make sure, maybe there's a typo. No. Okay, I think we're on the right track. Oh, no, we didn't. They got it backwards. Okay, maybe we can. Okay. Well, what am I missing there? Okay, I'm gonna strike through this. So we tried this. It was getting worse when we did our VDU. It didn't work out. So I'm gonna switch the U and the DV, and we're gonna try that. All right. So let me get rid of this. And we're just gonna, this is a case where, you know, we need to choose a different U and a V. So we tried that as u. So now let's let u be x. Then our du is going to be dx. We're going to let dv be, let me see, square root 5x plus 1 dx. Power. Let me see. If that were the square root of x, then when we go to integrate, you add 1 to the power. So let me see. Let's do 5x plus 1 to the power of 3 halves. Now, normally we would do over 3 halves, and I know we need to incorporate something with the inside. If we take the derivative of this guy, we're going to get our power of 1 half, but we're also going to have a times 5. So let's divide by 5 here. Let's put a 5 here, right? Okay, now if we take the derivative, the 3 halves comes down and they cancel. You have your power of a half. Okay. And then times the derivative of the inside, so times 5, and the 5s are going to cancel. Okay, that wasn't as bad as I thought it was going to be. So this, like, I was considering doing this u and this dv, but I was avoiding trying to integrate this guy. And then when I glanced at the result, I think they had this set up. So I was like, okay, well, let me go back and look at it again. I think, and we can manipulate this. We can rewrite this as 2 times the top over 15, right? But this is the core, right? And it wasn't as bad as I thought it was going to be. Okay. Okay, so now let's try this u and this dv in integration by parts, and let's see if we can simplify this and make it, make it something that we can actually integrate. So now the original x square root of 5x plus 1 dx, yep. We can now rewrite that as uv, all right, okay. So we're going to have this x times 5x plus 1 to the power of 3 halves. If we flip and multiply, there's going to be a 2 here, and there's going to be a 15 here, right? So that's our uv minus the integral of v. Again, that's 2 over 15 times 5x plus 1 to the power of 3 halves. V du dx. Awesome. Okay. All right. So I feel like this is easier because we removed the variable x, right? In the original, we had this function times this one. Now we just have 1. So I think that we just integrate. We can integrate again. We can actually evaluate the integral, right? The 2 over 15 could just come to the front, right? I just move it digitally because since I can, right? So like that, right? When it's a constant, you can just move it to in front of the integral. Okay. So now if we integrate that guy, I think we could just do what we did before. We add 1 to the power, right? Let's write it here. So we're still going to have our 2 over 15. Let's clean that up. 2 over 15x times 5x plus 1 to the power of 3 halves. That just comes down. Minus 2 over 15, okay? And then now, if we add 1, if we use the same technique that we did before, if we add 1 to the power, that's going to become what? 5 over 2? So we're going to have 5x plus 1 to the power of 5 over 2. We know we need to divide by 5 over 2. And last time, we also divided by du, which was, in this case, it happened to be 5. Right? And we can check really quickly by taking the derivative. The 5 halves comes down and they cancel. The power now becomes 3 halves times the derivative of the inside, so times 5, and the 5s are going to cancel, right? Okay, and just to kind of pull it all together, looks like we're going to get 2 over 15. Again, there's a plus c in here. We're going to get 2 over 15x times 5x plus 1 to the power of 3 halves. Let me see. If we flip and multiply, there's a 4 on top. I think 15 times 15 is 225. Okay. So minus 4 over 225. That can't be right. Hey Siri, what's 15 times 15?
15 times 15 is 225.
Let's keep going. That, and then we have what? X times this 5x plus 1 to the power of 3/2. Or is that a 5/2? I think that's supposed to be 5/2. Because we integrated, right? So 5/2. Did I make that change? Oh, that's from the original. Okay. Let me. That's what happens when you start jamming stuff in. Okay, so that's good, but I think this guy on the end is supposed to be 5/2. I think I'm losing track of it. Hang on. And I think the X. Let me just back up. I'm messing up on this final one. Getting mixed up with other components. Okay. So we flip and multiply. We get our 4 over 225. And then it's just 5x plus 1 to the 5/2. There it is. 5x plus 1 to the power of 5 over 2 plus c. I was trying to get that in there, but I kind of ran out of space. Let me move some of this stuff around. Let's make better use of my space. So I can move it here. Okay. I can move this guy next to it. And this plus c goes here. And that way it's not so jammed. And what we can do, let's shrink it down just a little bit. I mean, we can be uniform across the board. About like that. Okay, that's a little bit better. Okay, and so we get this as a result, right? But that was interesting because of that interval. So we actually did get a result. Okay, so let's compare it to our prepared notes. Let's see. So they did indeed let u be this and dv be this. So then our du was just dx. I think we got the 2 over 15, 375. I felt like that number was off. Oh, I did 15 times 15. It's 25 times 15. If you have 15 quarters, 16 quarters will be what, like $4 for 375? Okay, that's fine. Yeah. I did 15 times 15. It should have been 25 times 15. That's fine. And that's 75 right here. I think that was the only thing. 2 over 15x, 5x plus 1 to the 3/2, 4 over 375, 5x plus 1 to the 5/2 plus the constant. That is truly an adventure. One of the greatest adventures, right? Because I'm not gonna lie. Like I thought about this original U here. I thought about let this be U, but then when I thought about trying to integrate this, I was intimidated. I was like, maybe we're not supposed to do that, and so I was avoiding it. But then when I thought about it, I was like, well, if this were like x to the power of a half, you just add 1 to the power, divide by that new power. And then I knew we just had to account for the du, this guy here, right? So long story short, we got there and we got the same result. I feel like there should be questions, but it's okay. I'm just here if you want to talk about it. Okay, so we did this one earlier. I think I'm going to just use the result that we got earlier to evaluate this definite integral. So I'm going to go back. I know it was in the previous. I'm going to go back to example 2. Example 1. Yeah, this one, right? I'm just going to take this result and use it in this example. So I'm going to copy and paste. Let's go back to example 4. instead of doing that integral again, right? So then I'm gonna undo, let's paste. So the net integral is gonna be this guy, but instead of, well, we can keep this if we want to, but we want to evaluate this as x goes from 1 to 2, right? So then when we plug in when x is 2, I mean, we don't really need to see. I'm just going to get rid of it since we're doing a definite integral just for the sake of simplicity. Even if we kept the c, they would cancel when we subtract, right? Okay. So when x is 2, 2 times the natural log of 2 minus 2 minus when x is 1, it looks like it's just going to be plus 1, right? Because we're going to have 1, the natural log of 1, right? That something happens there, then we're going to say minus 1, right? So when we take the natural log of 1, this guy goes to 0. So then ultimately that becomes plus 1, all right? So then it looks like we get the natural log of 4 minus 1. And then I would use a calculator for that. And yeah, you see it here, right? And just to convince you, let's just go like this. Yeah, there we go. Camtech, yeah, this one. There we go. Okay. So we said the natural log of 4 minus 1, natural log of 4 minus 1, 0.386. Right? Okay. All right, let's see what else we got. Thank you. Okay. So let's give this one a go. Let's get rid of this. Let's get rid of this. Okay. So it says life science population decay. The rate of change in the population of bacteria T hours after an antibiotic treatment begins is estimated by this function here, where P prime is the rate of change of the population in thousands of bacteria per hour. Assume that when the treatment begins, the population consists of, 1.5 million bacteria. Find the population of the bacteria after 24 hours of treatment. Okay, so that's the rate of change. And then what is the total change in the population of bacteria from 24 to 36 hours after the treatment begins? Let me see. Are we going to do integration by parts here? U, dB? Okay, let's give it a go. So if we want the population after 24 hours, I'm thinking, because this P prime is going to give us the rate of change of the population. So I think if we integrate, that'll give us a population based on time. So we integrate, plug in T equals 24. And then I think the second part is asking us to evaluate that result as T goes from 24 to 36. Right? I think that's a fair game plan. Let me go view, seamless. We add a page. And I'm thinking that we're gonna need to use integration by parts to complete this goal, right? So we're given that P prime is T e to the negative 0.04 T, okay? So in the spirit of doing integration by parts, let me see, I'm gonna let my U, I'm thinking, we wanna simplify this, right? Okay, I'm gonna let U be T, and my dv be e to the negative 0.04 t. Okay, let's just try. So then our du is just going to be dt, right? And our v, if we integrate this guy, the integral of e is itself, so e to the negative 0.04 t, but we need to divide by, u prime, by u prime, by the derivative of the power, right? So divided by a negative 0.04, right? So then we check that if we take the derivative of e is itself times the derivative of the power, the negative 0.04 cancels, and we finish with our original, right? Okay, so this looks good. Okay, so then now we're ready to apply integration by parts again. Integration by parts says what? The integral of u dv equals uv minus the integral of v du, right? We chose the u and the dv. We found the du and the v, if that makes sense, right? Okay. So then for part A, the integral of p prime of t, okay, uv, so that's going to be t e to the negative 0.04 t over negative 0.04 minus the integral of v du. Okay, I'm going to move that 1 over the negative 0.4. I'm going to move that to in front of the integral. So double negative becomes positive, and it's going to be what? 1 over 0.04, right? And then we're going to have, so v du, we're going to have this e to the negative 0.04 t dt, right? Now this is a success because this is more simple, because in the original we had one function times a second, and again there's a dt in there, and there's a dt here, right? We had two functions, the t and this guy. So now at this point we just have the one function, right? And we can integrate that. Okay, so then if we keep going, we have this negative t e to the negative 0.04 over 0.04 plus 1 over 0.04. Now, the integral of e is itself, so we're still gonna have our e to the negative 0.04 t divided by the derivative of the power, so divided by this negative 0.04 plus a constant for right now. Okay. Okay, so can we could let's so right now at this stage, our claim is that P of t, I don't know if that's going to help us. Let's just leave it the way it is. Okay, so right now our P of t is, we got this negative t e to the negative 0.04 over 0.04 minus 0016. Is that what that is? 0.0016, like that. Okay. And we still have this e to the negative 0.04 t. Now we want to solve for this constant, right? We were given that the population started with 1.5 billion bacteria. So that means when the time is 0, so then when time is 0, the population is 1.5 million, right? But if we plug in t equal to 0, then it looks like this first term goes to 0. Okay, I thought the second one might go to 0 as well, but it looks like it becomes, so we're going to have minus, that's going to be a 1 on top. That's fine. Are we missing a T there? I think we're missing a T. Yeah, there should be a T here. T there, T there. Right? Yeah. Okay. So when T is 0, we get a 1 on top. So it's basically 1 over the 0016 plus a constant. And again, that result equals 1.5 million. Right? Bacteria. So then we can solve for C. So from there, we get that C equals, why is it not 0? I feel like we're missing something. I feel like that should have gone to 0. But I think we're okay. Let's just crunch that number. Let's just crunch the number. Okay, so we're going to say, let's see, 500, 1, 2, 3, plus 1 divided by 0.0016. 625, okay. So 1 divided by 0.0016 is 625. So then C we get is 1,500,625 bacteria, right? So now we have an expression for our population based on time. It looks like it is, now we could fix these numbers, right? Because if we're divided by 0.04, 1 over 0.04 is the same as 25, okay? So then that's gonna become negative 25 T e to the negative 0.04 T. I think that one is 625, so we're gonna say minus 625 e to the negative 0.04 T plus 1,500,625, right? That's our population based on time, you know, given everything, given our initial conditions. So then, so we can highlight this. No. I think part, actually, they wanted the population after 24 hours, so we don't need to highlight this yet. So then P of 24, it's 25 or 24, it should be 24 hours, right? Yeah. So basically we plug 25 into that. I think I'm gonna type that into my y equals, type it as a function. So what I'm gonna do is go here to my y equals, I'm gonna put negative 25 times x times e to the power of negative 0.04 x, okay? Then I'm gonna say minus 625 times e to the power of negative 0.04 x, okay? Then I'm gonna say plus 1,500,625, okay? All right. Okay, so then what I'm gonna do, I'm gonna call on that function and I'm gonna evaluate it when t or x is 24. After 24 hours, do we have decay? The rate of change, let me see. The rate of change in the population T hours at the antibody, right? Antibiotic, right? So it should be killing the bacteria. So it's going down, which is a good omen, right? Because it looks like we started with 1,500,625. Now we're at like 1,500,155 or 156, right? Okay. So I'm just going to say that this is approximately 1,500,000. I'm gonna say 156 bacteria. Okay, that's a good omen. It's going down, right? The population of the bacteria should be going down because we applied an antibody. Okay, and then they want to see the total change for part B. What's the total change in the population of the bacteria? All right, from 24 to 36, right? Okay. So let's add one more. Evaluate that result as T changes from. So I'm just gonna write it shorthand. That was part A. Yeah, there it is. Okay. So this is for part B. I'm just gonna evaluate P of T as T goes from 24 to 36. All right. So I'm gonna plug in 36. We already plugged in 24. I'm gonna subtract those two results, and that's gonna be the total change, right? So what I'm gonna do is just call on that function I put in. Let T be what, 36 minus that same function when T is 24. And 100. So in that amount of time, it looks like about 108 bacteria have like died or gone away. Yeah, 108. I think that's correct. 108. So this is approximately 108 bacteria. And let's see, how do we do? I guess we should be able to get that on this other page. Let's go like this. Let's go like this. I think that captures everything. We're just gonna shrink this down just a little bit like that. And let's move that about there. And I just want to try to expand it to fill up as much of the page as possible. That looks good. Okay. Delete. And let's go view, single page. Let's see. All right. So let's see, how do we do? Okay, I think we got this kind of result. It looks familiar. All right. Okay, let's go with it. Okay, we're off. Let me see. This population at T hours is given by this. We got a different C. That goes to 0. That was negative 625. Okay, so they're doing theirs in terms of thousands of bacteria. So they got, I think we still got something different now. I see, looks a little off. 1 million, okay, after 24 hours. Let's go back. Let's see if we can find, I think we made a mistake somewhere. We need to find it. Okay. Let's go view, seamless. So let's see if we can find it right here. 625. Did we do that properly? Let's go here. We're not far off. I think we just did a calculation error somewhere that we need to find. So if we said this 1 divided by 0.0016, 625, yeah. Maybe that's off. Okay, let's see. 0.04 times 0.04. Yeah, that's fine. What else? What else? It says we started with 1,500,000. The first one is gone. That's going to be a 1 over that. See, we're getting 625. Maybe, I feel like theirs is off. Because we get our 625 there, but on the right, we have 1,500,000. Where they have 1.5, 1,500. So I feel like theirs is actually off. Right. Because I think we got all of this. 25, we got that. Did we get our negatives? Yeah. Yeah, we got that. But right here, the 1,500. I think that's supposed to be 1,500,000. I think theirs is off. Thus, the population of the bacteria after T hours is given by this. Thus, the population of bacteria after 24 is approximately this. Yeah, I think theirs is off. What's the time? The total change in the population between is approximately 107,000. I think I'm going to challenge their result because right here, they never addressed this 1,500, right? The population is supposed to be 1,500,000, not 1,500. And I was like, well, I was thinking that maybe they changed their terms, like they did theirs in terms of thousands of bacteria. Right here. The population consists of, assume that when the treatment begins, the population is 1,500,000 bacteria. I think theirs is off. I'm going to challenge it and stand by what I got. Again, I feel like our result makes more sense as well, because if we apply antibody to these bacteria, you would think that it would kill off the bacteria. All right, so the number should go down. So let me see something. Yeah. So if we're starting with 1,500,000, oh, ours still went up though. Ours still went up. Let me think about it. I still gonna stand by ours because they still never address that one. They did 1,500 where we did 1,500,000. And that's what's really throwing it off. And I'm thinking that they have a typo. I really feel like there's a typo. Let me look at it one more time. You add that, I get this. So it increased by, and we got 108 and they got 107. So the second one was close, but it's that first one that's a little bit, iffy. And again, usually when they kind of change the units like that, they say, hey, this is in terms of thousands of bacteria. They address it, but they didn't address it with this. We find P of 0. Yeah, I'm going to challenge theirs. That's the T hours is given by. Let me see. Maybe I'm missing something else. Let me check one other thing. The rate of change of population T hours after antibiotic treatment begins is estimated, where P is the rate of change of the population in thousands of bacteria. There it is. Okay, that's what I was looking for. In thousands of bacteria per hour. So this is expressed in thousands. So we do need to do what they did. Okay, I'm glad I kept going. Okay, so because it's in thousands, then what they did is correct. Right? That's what I was looking for. So let's make those adjustments. Seamless right here. Because that expression is in terms of thousands, this guy, I'll do it in purple, I guess. Instead of, here, let's strike through it. Instead of it being 1,500,000 to make the units correct, we need to do, if we go doing it in terms of thousands, it is indeed 1,500, right? Okay, that's better. Because again, the original formula was in terms of thousands, all right? So now if we add the 625 to that, let's just do it here. Okay, we get our 2125, right? Okay, I feel better about that. So I'm going to strike to this and put 2125, right? Again, we keep in mind that everything's in terms of thousands, okay? So that's really 2 million, right? Whatever, yada, yada, yada. Okay, so then here, this guy becomes, so we solve for C, right? We get the 2125. Okay, so then also adjustment we need to do is right here. This guy right here, let's see, I just want to get there quickly. It's just this one, let's delete. Okay, and that's supposed to be 2125. Okay, so now I'll just do it from scratch. So let's call on the function and evaluate it when T is what, 24? We should get like 2 million, I think. So that's 1,655,956 bacteria, right? Okay, so let's strike through this guy. And with that adjustment, when we realize that this formula was in terms of thousands, then this is going to be 1,655,956 bacteria. All right. And then for the second part, we're going to say 36 minus when T is 24. Okay. And we still get approximately the 108. Okay. So we can say about that one. But yeah, it was just our units were off. We had to straighten out our units. That was the trouble there. Okay. 1,655,956. See it. All right. So you see it here. Again, this is in terms of thousands, so it means this guy here. Okay. Yeah, so I had to keep digging. We did have our units off. So okay. We're gonna go ahead and wrap this up. Let's go to view and single. So we got to the bottom of that one. I think B, we got a similar 108,000, right? 729. So again, in terms of thousand, I keep forgetting the unit of 1,000. We can see it here. There it is, 729. So let's strike to this. We get 107,729. And it's an approximation. Okay, and I think we're good right here. Okay, well, that was fun. I don't really, let me glance at the next one. Evaluate this to find the area of the shaded region shown below. To me, that last one would have been better if they just, it's fine. I was like, why not leave? But the reason they probably didn't leave it in millions, because now you're going to be working with these massive numbers the whole time, and it just makes it worse. So they converted everything to in terms of thousands, and you just have to be cognizant as you do the calculations that things are in terms of thousands of units. This one looks like it's integration by parts, and just glancing at it, it looks like we're going to be doing integration by parts at least twice. Just for the sake of time, because I think I am burnt, like I can't really focus anymore. But just looking at it, it looks like integration by parts twice. Like if we let U be X squared, and this is our du, yeah. So then when you find this is our U and this is our dV. When we go to find du, it drops by a power, and then I'm pretty sure we're going to have to do integration by parts a second time to calculate the integral. I'm going to piggyback off of my prepared notes just for the sake of time and my sanity. So notice it did let u be X squared, and dV is this guy. When you integrate, you get here. And notice we still have an X there, right? So then it's going to be uv minus the integral of v du. And it's going to kind of be a repeat. We're going to have to do integration by parts a second time right here. This guy, we're still going to have to do integration by parts again. All right. So we're going to let u be 2x, dv be this guy. And then from there, we should be able to finish it. All right. Eventually we get here. Okay. We can factor out all those negative e to the negative x's, and it'll look like this. And then we're evaluating the integral as x goes from 0 to 7. Okay. Okay. I think that kind of brings us to the end. Oh, there's another one. Okay. So now I just want to kind of mention this because we are out of time, but if we try integration by parts here, you're going to notice a pattern. And so the suggestion is to use a table. We have a repeated derivative. The sign of the products. So we see add the products along the arrows, making our alternate sign changes to obtain this guy, right? So we have f of x and repeated derivatives, g of x and repeated integrals. Okay. And the sign of their product. How does it alternate? Does it always alternate? I think it always alternates. I'm not sure about that. Let me see. So f of x and the repeated derivatives, right? So the first thing that you're choosing, because remember in the previous one, we noticed that the powers were going down until they were gone. And then the repeated integrals with e to the x, it was going to be the same thing each time. Let me see something. Sign of the product. And I think the sign is alternated because of that part that says the minus the integral of v du, right? I think that's where it's coming from. Okay, so then. So all of those are basically multiplied by e to the x. Okay. Well, that was it. That's interesting. Okay, we'll have to try something like that another time. Okay, so, that kind of brings us to the end of integration by parts. All right, guys, so I am spent. I can't stay today because I need to get back out there with a little bit of sunlight that I have left. If you have questions, you're going to have to email me, and it's going to have to be that usual thing. Like, I'll do the best I can to respond over the weekend. If not, we do meet next week on Monday and Wednesday. We are going to be taking the exam. So more than likely, I'm just going to make myself available for questions on Monday and Wednesday next week while you guys work on your exam. I want to say the following week is review for the finals. So we'll take some time to review there. And then we're going to be wrapping everything up, okay? I'm proud of you guys. This is not easy. You've done it. Just finish it. Your grade and everything, your glory is sitting there waiting for you. You just got to reach up and take it, right? You just got to take it. It's just there waiting for you. So hopefully you devised a plan to get the stuff finished and submitted. You've asked me questions. You're working together. You're working with the tutors, doing the things you need to do to just keep moving. Okay, guys? So with that brings us to a close for the new content. Are there any burning questions before we go our separate ways that we can kind of answer kind of quickly? Any burning questions? Okay, let me go ahead and make a copy of this content available. Yep. Okay, so when this bar finishes loading, you'll get a copy of what you see here. And if there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, have a great weekend, guys. And I'll see you next week, same time, same place. Take care. Peace. Okay. Guys, here one more time.